Quadratic spaces over finite field are the easiest to classify. If F is a finite field of odd cardinality, then all regular quadratic spaces over F are uniquely determined by their dimension and discriminant. This is not necessarily true for quadratic spaces over other fields, for example over R, by Sylvester's laws of inertia, or over p-adic numbers. Over p-adic numbers, we'll have to introduce a new invariant called the hash symbol, and together that with dimension and discriminant, we will be able to classify quadratic spaces over QP. But for finite field, just dimension and discriminant, that's sufficient. So let's see why. Clearly, if two spaces are isometric, then they have the same dimension and the same discriminant. Now we want to show that the converse is true, so let's suppose that the dimension and the discriminant of these two spaces are the same. We want to show that V and W are isometric. And this just comes from the following idea, that every quadratic space over finite field is isometric to one of this form. It can be written in this form, 1, 1, 1, 1, and then there's discriminant, so we want to understand why. Every quadratic space will have an orthogonal basis, so we can always write it in this form. That we know. Now remember that these AI are only determined up to a square. So then, if delta is a representative of the non-square class, we know that then this is going to be equivalent to this. Now the key thing we need to prove here is that there only needs to be one delta. We only need one delta. Because if we can prove that, then we can see that delta must be congruent to the discriminant mod a square. Why is that? Because the discriminant is just going to be the determinant of the gram matrix, right? In this basis, the gram matrix is just diagonal with entry 1, 1, 1 and a delta, so the discriminant is just going to be delta up to a square. Thus now what we need to show is that we only need one delta, and to show that, what we want to show here is that this space, whenever we have two delta, then we get a space that is isometric to 1, 1. And let's see why. Now we claim that it suffices to show that delta is represented by this space 1, 1. And why is that? Because if we can show that, then that means that there is some vector W in this space, right, whose norm, the quote-unquote norm, is delta. And so if we change the basis to start with W, and then another basis element, then we see that the orthogonal to W, which we can do because the span of W is regular, then we see that in that new basis, new orthogonal basis, the space 1, 1 is gonna be isometric to this. Now, because they're isometric, they must have the same discriminant, but the discriminant of this is 1. Discriminant of this is delta multiplied with something. They have to be congruent to each other modulo a square, but delta is not a square. So this other element must be congruent to delta modulo a square, so that must be delta up to a square. Thus we see that it suffices to show that delta can be represented by the space 1, 1, and that's exactly what we are going to do now. Now observe that this is going to be isometric to beta comma beta for any non-square beta anyway, so I just need to show that 1, 1 represents some non-square. And for that I just need to show that these two sets aren't the same, right? Actually, I need to show that there is this set doesn't contain this. But because they have their same cardinality, this is equivalent to showing that they are not the same. So I just need to find an element in one, but not in the other. So for example, I have 1 lies in here, but 1 doesn't lie in here because 0 is not a unit. So these two sets are distinct, so I can find some element in here that it's not a square. Thus I can write B as 1 plus y squared, right? 1 times y squared, this is represented by 1, 1. So that means beta beta is isometric to 1, 1. And because beta is also a non-square, it's isometric to delta delta, so delta delta is isometric to 1, 1. And that's coming back here, we know that in this expression we only need one delta. That delta must be congruent to dv. So we see that every quadratic space over a finite field can be written as this form, 1, 1 and then dv. So in particular, if w and v have the same dimension, then they have the same number of 1 here, and if they have the same discriminant, the last entry is the same, so they are going to be isometric. And thus quadratic spaces over a finite field are uniquely determined by their dimension and discriminant.